Hello and welcome to this video. So in this video, our task is to find a state space representation of this system. Now notice that generally questions that have to do with finding state space models, the question always goes find a state space representation, because there are typically several state space representations one could have for this. You have the phase variable form, dual phase variable form, Jordan canonical form. There are several forms that one could have, and we'll just come up with one here. So the first thing to do is to come up with a set of state variables. Now, one thing you get to know is that the number of state variables is the least number of variables you can use to completely define the system. That's called your state variable. Now, generally speaking, if you have an electrical system like this, the easiest way to go is just think of the number of energy storage elements you have here. And that means we'll have three state variables should be the minimum we can have for this. And in fact, let's just define them this way. Straight up, let's just use 1, 2, 3 as our state variables. Let's call this VC1. So let's call this capacitor C1 and capacitor C2. And then this would be inductor L. 1 Henry, 1 Farad is convenient. Yeah, so I picked this example because it's kind of convenient to have those parameters in there. So let's define our let's start from this. Now, we want to use a differential. The reason why we're interested in differential is, remember that your state space representation, you always have your first differential is equal to a certain A matrix, which is called your system matrix, multiplied by your state variables, plus your input matrix multiplied by your inputs. And then you have your output being equal to your output matrix, plus what you call your feed forward matrix or your forward transition matrix. That's your D. Okay, so this is the system we want to be. So since this is first order differential equation, and then we already have that our let me see, it's VL is equal to L di dt, and we know that our VC, IC now is equal to C dV dt. Okay, so since we already know these are first order differentials, so why not let's just simply use this. So let's take the first one. Since we have our L first of all here, let's say that we could say L di dt, but why call it L di dt? Why not just simply say di dt? So the IL dt, because that's the current flowing through the L dt, will be equal to 1 over L, the integral of, 1 over L multiplied by V L, okay? 1 over L multiplied by VL, because VL is L di dt, okay? So 1 over L multiplied by VL. But the question now is, what is VL? Okay, let me just write it there, VL. Now, what is VL? Now, to make our life easier, we could leave it as VL, but then it doesn't help us that much because VL is not really defined. However, we do know your VI, and this term here we've labeled C1. So we know our C1. So by the way, it's important to specify what you want your polarities to be, because that will determine whether things are positive or negative. Okay, so VL, let's say VL is the voltage in that direction from right to left, okay? And our VC here, because of the, you can see the polarity I put in there, it will get a little too messy if I put in things there. So let me take off that arrow so things don't get too messy over here. So I think it's kind of obvious that you have VI minus VC1 will give us will give us VL. Does this help us? Do we know VC1? Not yet, but let's just leave things at that for now. And let's write the other equations that we have. So let's go to the C dV dt. Let's talk about VC, the current going through capacitor C1. What direction do we want that current to be? Well, we could say it is going in the direction of I2. Okay, we could say it's going in the direction of I2. That's our choice. Since the polarity, selected this as our polarity, let me also select this as a polarity over here. Excuse me. Let me select this as polarity over here. So we have our VC1. So let's say the VC1 dt will be equal to 1 over the capacitance multiplied by IC. So what is my IC? Now, if I say IC is going in that direction, if I decide to make it go in that direction, then we can define our IC as being I2 minus I1, because IC1, now that IC1 is going in the direction of I2. So it could be I2 minus I1. Okay, so we have that. Then let's have our third expression. Third expression will be our dvc2 dt. And then this, again, we need to specify what we want the direction to be. We could decide we want the direction to be to the left in the direction of I3. If we decide that, then it can be 1 over, I should write this as C1, 1 over C2 multiplied by I3 minus I2 minus I2, okay? So I3 minus I2, because again, we're specifying that it's going in that direction. We're looking at the current going through capacitor C2. So just give me one moment. Yes, so I think I've done this wrong. Okay, so I've done this wrong. Let me explain why it is wrong. If we had a simple system here, you have a plus, you have a minus, and we had, that's a voltage supply. Let's say this is a DC voltage supply. We sent it through a resistor, and after that we had a capacitor over here. And we close our circuits, pardon the drawing. Let me just ground this lower end over here. So this is our R, this is our C. If we wanted to take a walk around this system, I will call this VI, then we will say that our, let me give myself some room to write. We have our, according to KVL, your VI, so we will typically take this as our potential and this as our potential. Now, why do we take that? We take that because we assume our current is going in that direction. So if current goes in that direction, then the potential across this, the potential that will be induced across the resistor will be in the opposite direction, okay? So it will be minus IR, and the potential that will be induced across this will be minus C divided, well, yeah, okay, so will be minus VC, let's just put it that way, will be minus VC. Now, and that again is because you have, once you have a current flowing in one direction, you have the potential in the opposite direction. So back to what we had over here, because I defined this as my positive above and negative underneath, that should have meant I1 is the direction of the current. So I should have had I1 minus I2. So since I did I2 minus I1, I'll just make this a negative over here so that that sorts out for that. And same thing you have on this end. If I put my positive on the left side and the negative on the right side, that means the current is going from right to left, in which case I3, we're going against I3, we're going in the direction of I2. It should have been I2 minus I3, so I'll put a negative over here. I think now we're correct. Just take one final look and see. Yes, okay, so this seems good now. Okay, let's go on. Now, if you look at this left-hand side, we have a single differential. We want to come up with our state equations. You have a single differential on the left-hand side. That looks good. But if we look at the right-hand side, we do have a problem. For this first expression, we're fine. VI is given to us. VI is our source. Okay, so that's perfectly okay. VC1 is one of our state variables. So that is also perfectly fine. This first expression the first equation is perfectly okay. Second equation and third equation, however, have a problem. You have I2, you have I1, you have I3, you have I2. Those are not part of our state variables, so they are not very useful to us over here. So can we try to find out what I1, I2, I3 are? If we can find out what they are, then we are good to go. Okay, so which will be the easiest to find here? Well, many of them are effectively not that difficult to find. We could start from, okay, let's start from let's just go ahead and start from I1. We know IL is one of our state variables over here. So we know the current going through this inductor. Okay, so just for a moment, I want to check current. The current going through the inductor has to be going to the right. Did I use that correct? Okay, that's fine. I just used voltages, so that's okay. I didn't use the current. So the current going in is current to the right. In other words, just want to keep this diagram on the left still visible. So I'll write on this left here. It means that our IL is defined as being I1 minus I3. Okay, so IL is I1 minus I3. So you could say I3 is IL minus I1, in which case we now have everything in terms of just I1 and I2. I1, I2, and IL. Okay, once I have this expression here, I could express, from this, it means that our I3 is equal to I1 minus IL. So I can express I3 in terms of IL and I1. So I just have I1 and I2 to deal with now. Let's move on to I2. If you move on to I2, if you look at this expression, this is VC1, this is VC2, and then you have a voltage on this here. Now we can use KVL in this loop to get our I2. I2 is the only current that goes through this resistor. So if we know the potential across this resistor, I will simply divide it by this resistance. We can arrive at my I2. Now, what is the potential across this resistor? Potential across this resistor will be equal to, so we could say our I2, I think this should be quite, I think I can write it in one go without you feeling confused, will be equal to VC1 minus VC2 divided by that resistance R, which is 2. Okay, so that's my VC1 minus VC2 divided by the resistance here, which is 2. So that gives me my I2. VC1 is a state variable, VC2 is a state variable. So I2 we have represented in terms of state variables, and we're fine. I3 is not quite there yet, so I1 is now what we are left with. Okay, once we know I1 in terms of the state variables, then we are good. I1, right? Yes, I1. Okay, we know I3. I3 is the other thing we can compute. So I'll leave out this expression over here, or let me just leave it be. I can come back to it later on. Let's look at this third loop over here. We can run a KVL on this loop. We can run a KVL on this loop, and that will help to give us the, that should give us the current we have flowing in here. So we know the potential across this, resistor will be VI. Do I want to do that? Or, okay, sorry, just give me one moment. I'm trying to decide the best way to define this. You have your V1, you could subtract our VC1, and that gives us this potential here. We know the potential here. Actually, you get exactly the same thing. So it's perfectly fine. So we know the potential at this point here. Potential at this point here is simply equal to VI. We know the potential at this point here. Now we're going to assume that the potential at this point down here is 0. Okay, we should have been given a ground somewhere, but we're going to assume the potential down here is 0. If the potential down here is 0, then we know the potential through this place. We know I2 is flowing downwards through this. So what you have here is simply 2I2. I hope that is clear. That's the current going through this resistance. So what you have over here is 2I2. That means you can get the potential going through this resistor. I3 is going from left to right. So it could be VI minus 2I2 divided by this resistance. So my I3 will be equal to VI minus 2I2 all over 2. Now we know what our 2I2 is. 2I2 is simply equal to, or I2 is equal to this expression. So it means my I3 is equal to VI minus VC1 plus VC2. And that divided by 2. So that's our I3. From that, we can get our I1. I1 simply being equal to I3 plus IL. So, okay, let me just take this to the right a bit. Let's just say I1 is equal to I3 plus IL. So, if I1 is equal to I3 plus IL, and we already defined our I3 over here, then add IL to this and you have your I1. So let's go ahead and let me now try to write out the state equations. I want to give myself a little bit of room, but at the same time I don't want to lose what we have written. So I'll just try to write it from down here. So you have your dIL dt. That should give me my first state equation. We already had that before. Was equal to 1 over L. L is 1, so it's just simply equal to VI minus VC1. Okay, that's good. Let's go to the second state equation. Second state equation says the VC1 dt is equal to 1 over minus 1 over c. So 1 over c, I'll just make it I1 minus I2. 1 over c is 1. So that will just simply be 1 into I1 minus I2. I'm taking a negative sign inside. I1 minus I2. What is I1? I1 is this whole thing plus IL. So I1 minus I2. So it could be IL. Let me start with IL. That'll be IL plus this expression over here. That's VI over 2 minus VC1 over 2 plus VC2 over 2. This whole expression here is my I1, and then I am to subtract my I2 from it. Yeah, I'm to subtract my I2 from it. Now my I2 is equal to, subtract I2 is equal to this expression over here, minus VC1 over 2, and then plus, because we're subtracting, VC2 over 2. Okay, so this now comes out very nicely as being IL. I'll collect like terms. You have VI over 2, I'll put that last, minus VC1 plus VC2, then plus VI over 2. That's our second state equation, okay? So if you want your VC1 dot is equal to this expression. Let's now go to the third equation. Okay, so the third equation, VC2 says I2 minus I3. Okay, so I will not write the dt. I'll just simply write it as VC2 dot is equal to let me just confirm that, I2 minus I3. And taking negative sign in, that becomes I2 minus I3. I2 is VC1 minus VC2. So I2 VC1 over 2 minus VC2 over 2 minus I3. I3 is this expression over here, minus VI over 2 plus VC1 over 2 minus VC2 over 2. And once again, this is this can be simplified to give us VC2. Well, let me write it on the same line just so that I have the space down to work. So this is equal to there's no, so yeah, so it's equal to VC1. There's no IL term in this. VC1 minus VC2 minus VI over 2. And now we have our state equation. So let's just write it formally. You have your IL dot, VC1 dot, VC2 dot. And it's because I was going to write it out in this form. That's why I decided to always write my VI last, because that will make it a lot easier to just write it out in this way, or at least it could be a lot clearer. So IL is simply equal to, oh, okay, here I forgot to write my IL last. It's got to minus VC1, so 0 IL, 0 here, minus VC1, minus 1, and 0 VC2. Okay, let me write the others before I close the square bracket in case I didn't leave enough space. For VC1 dot, you have 1, minus 1, and 1. Okay, so I think I can close this off. I'll definitely have enough space to write this. The state variables, IL, VC1, VC2, plus, is this a plus? Yeah, well, let make it a plus, because we always have it as plus BU. If there are negative terms, I could put them in here. So the first one is a positive term, 1. Second term, where's the VI? VI term is 1 over 2. And the third term here is negative, minus 1 over 2, multiplied by VI. We're left with this third row here. VC dots, we have it being equal to 1. Sorry, this should be a 0. No IL term, then a 1 VC term, and VC1, and then minus 1 VC2. So this is our state. These are the state excuse me, these are the state equations for the system that we're given up there. These are the state equations, but we are not done yet. We still need to know the output equation. So the question is to specify what the output is. Here we have a V0 in the figure, so let's take it that that is our output. So if this is our output from here, if you don't mind, let me as well write out what the output will be from here, from what we can see. I will erase this so that it doesn't disturb the flow later on. I'll write it below later. I'll write it below shortly after this. So our V naught, that's the potential here, will simply be equal to, I think it is clear that it's equal to I2 multiplied by 2. So V0 is simply equal to 2I2. I hope that's straightforward. What is I2? I2 is VC1 minus VC2 over 2. So, in other words, my V0 is simply VC1 minus VC2. So let's take this off and let's go and write that down. So we said that our V0 is simply equal to 2I2, which is equal to VC1 minus VC2. So we have that expression, which I've probably done this before writing these state equations over here. So that gives us our output equation. Now our output equation is simply V0 is equal to, open square brackets, we have no IL term, 1 VC, 1 term, and minus 1 VC2. And we will multiply this by our state variables, IL, VC1, VC2. Is there any forward transition matrix? Well, we don't have any VI term here. So if you want, you could say plus 0, or you could just leave it out like this. So this term here and this term are our solution. That's the state space representation of this system. See you in the next video.